This video is going to look at mass, weight, and weightlessness, and this is where we want to kind of reiterate what's the difference between mass and weight, and what do we mean when we talk about weightlessness. So jumping into this, there's two kinds of mass, and this is getting a bit technical, a bit beyond what you would normally hear in an introductory physics class, but I want to plant these seeds. You don't really need to know this if you're just going to, this is the last physics you're going to take. But it is kind of interesting to talk about some of the things that are, still developing potentially in physics. So mass is roughly the amount of matter or stuff in an object, but that isn't the most precise definition. More precisely, we actually have two definitions of mass. First is the inertial mass, and this is the mass associated with an object's resistance to motion. And we found this, or we find this, or calculating this by using the equation net force equals ma. So we can take an object, we can measure how much force we're applying to it, and we can see how quickly that object accelerates, right? We can just measure how it's moving. And we can divide those to get this equation for mass, or more commonly, we can use this definition, net force, or mass equals net force over A. So if we calculate net force, we calculate A, we can divide them to find the mass of the object. That defines the mass of an object. We can also define mass by gravitational mass, and this is the mass associated with gravitational attraction. So as we've said before, the gravitational force attracts any two objects with mass. So if we use Fg equals g m1 m2 over r squared, and we use this, rearrange, solve for one of the masses, and use this to calculate the mass of an object, that will give us another way to calculate mass. Every single experiment we've done seems to show these as identical, meaning it seems to show that gravitational mass is the same thing as inertial mass. But what's interesting in physics is we have no reason to believe that has to be the case. They seem to measure the same thing, as in both cases, bigger objects exert bigger gravitational force. Bigger objects are harder to change their motion. Calculating them, we get that specific number of some number of kilograms. And it's always the same if we do both tests on an object. But just in the fundamental rules of physics, we don't have a rule that says these two masses have to be the same. Now, like I said, we believe they're the same, we believe they're measuring the same thing, but at the moment we don't have that proven. So it's just an interesting aspect of one of the parts of physics that is still theoretically being looked at. Let's differentiate those masses, which again, we're treating them largely the same. We'll treat them the same in this class. But now we're going to differentiate that from weight. And weight is the measure of the gravitational pull on one object by another object. So this is most commonly the pull of a planet, a star, or another celestial body. It's like a moon, an asteroid, something like that. Those things that have really big masses so they can have a meaningful gravitational pull. But it can be any object. We can technically talk about the weight of this stylus with respect to me. So how strong my gravitational pull on this stylus is would be the weight of this stylus with respect to me. It's a number that's essentially zero, so we don't usually talk about that, but technically those would be considered weights. However, like I said, in everyday conversation, certainly we're talking about pull towards the Earth. And in physics, everyday usage of, if we say weight, we mean pull towards the closest planet or star or whatever is the dominant gravitational force. In this case, you can use Newton's universal law of gravitation to calculate weight, or you can use this equation mg but just make sure you use the proper g. So if you're farther from the Earth, you're not using 9.8. If you're on a different planet, you're using the right g, and remember this g can be calculated by saying g times the mass of whatever object it is times the radius or the distance from the center of that object. Now, if that's weight, and if we've talked before about how on the International Space Station, astronauts still feel about 90% of the gravitational force that they feel on the surface of the Earth, what do we mean when we say weightlessness? Well, the only way to be truly weightless is to be infinitely far away from every other object. Because, if you look at Fg equals g m over r squared, well, unless an object has zero mass, which if we're talking about like weight being pulled toward the nearest gravitationally dominant object, that object's going to have some mass. So the only way to get Fg weightless, to have no Fg, is if r goes up to infinity, meaning that this fraction goes to 0. So what we usually mean when we say weightless is there's no apparent effects of weight, meaning that an object does not appear to be preferentially, that's a big word, but that just means it doesn't, if you let go of something, it doesn't get pulled in one direction or another. So we don't say this pen is weightless because if I let go, it falls. But if I was on the International Space Station and I let go of this, it would sit in the same position relative to my hand. And that's why we say it's apparently weightless, because it's not being pulled. It does not appear to be pulled towards the Earth. And this apparent weightlessness occurs when everything is in free fall, meaning everything is falling at the same rate, and so objects do not appear to be pulled in one direction or another. If I'm falling towards the Earth, like skydiving, and I let go of this pen, well, I'm falling and the pen is falling and they're both falling at the same rate. There's nothing pushing us in one direction or another. So it would look like it was floating in front of my hand. And this is how we model or give people some practice with the sensation of weightlessness. They'll take a plane, they'll go way high up, and then they'll basically put the plane in free fall for a while. And so for this whole section, while the plane's just kind of falling towards the Earth, everything inside the plane is falling at the same rate. And so everything stays kind of fixed. If you let go of that, the pen, it'll just stay there. And you can see this if you look up like 0G planes. You can see an example of this videos online. So that's what we mean by weightlessness. We don't actually typically mean no gravitational force. We just mean everything is falling, so it doesn't look like anything is moving relative to one another.